Hello again. Just before we leave this machine code assembly language software debug, we may as well, while we're here, have a look what's going on before we move to the higher level language. As you can see here, we can do our own assembly and we can do our own unassembly and we can just dump machine data. Let's have a look here. We'll try the D command first and we'll have a look where was that video ROM. You have to watch my ROMs and RAMs sometimes when I'm speaking. We're going to look at the video ROM. Let me look at my notes. It began at C00 hex, so we'll dump some of that first and see what let's see what we get. We're going to dump C000 hexadecimal. That's the page number. We'll start at the very bottom of it. And when we hit this button, you can see here all we get is a big string of numbers. Now, those numbers, they don't always mean the same thing. It depends where they are and what they're doing. But we can see here where we're at. Obviously, whoever wrote the software to run this VGA card wants to put down who they are, what they're doing, and all the information you might need. You see that jumping out onto the screen during boot. Okay, that's actual machine code there. Then we can have a look at what it would look like if we were to turn it into the mnemonics, which is the next level up. The mnemonics are actually the instructions that go back and forth to the processor. So this time we'll use the U command. We'll unassemble this and see what it all means. Let's just start there. Now you can see we've got the address locations. One of those numbers that we saw there in that big block of numbers, and here's what they mean to the actual processor. These are various instructions. These are sometimes registers, sometimes they're locations, sometimes they're data. Push just means move something onwards. Store SB, I think it's store the SB register. Increment the AX register. Jump 9 spaces ahead. I think you can have jump forward and jump backwards. This assembly language here, or these instructions, are dedicated to the machine that you're working on. When you write your high level languages, your C++ and these kind of programs, when you see it going to assemble, it actually has to assemble it to suit the processor you're going to use it with. The beauty of C++ and languages like that, they can assemble for lots of different types of processor, not just the one. This is what all your programs get turned into eventually. They get assembled into whatever language suits the processor you're working with, and at the end of the day it all ends up in memory just a list of numbers. And remember, these numbers don't always mean the same thing. It depends where they are. It depends whether this 40 is an actual instruction or is it just a bit of data that's being put out. It depends very much where it is and what it's doing. So there's no fixed meaning for a lot of those numbers, but there is a fixed meaning for these instructions. Okay, that's just a little by the way. So we'll move on now. We'll quit out of this and let's go and have a look at a sort of a higher level, more user friendly language. We'll quit out of this and we'll go to Qbasic. Now this looks more like your editor, similar to what you might see in C++ or an even higher language. Most people would be familiar with C++. This is a precursor to that. What we can do here is we can do a lot of things just the same as we did with the machine code and assembly language. What we can look at here is, let's for example, we'll try and put out something to our parallel port here. We'll have a little go at it. All we've got to do here is type out. Now I'm going to put in the decimal number here. You can put in the hexadecimal number, but it needs no more syntax. If you convert, what is it, 370, let's have a look. Oh, 378. If you convert 378 hexadecimal, you'll find in decimal that that's the same as 888. We can convert our hex now to decimal. just to save on some syntax. We could use either decimal or hexadecimal there, only we have to tell this software now whether it's a hexadecimal number or a decimal number. What should we put out to this port? This time we try number 8, and let's see what happens. Oh, hang on, we've got no comma in here. Talking about syntax. We've got to put a little comma in here. Okay, and that's it. We know the syntax is right now. Now to run this program, we're just telling it what to do at the minute. Now we go to run it. Okay, we go to start, and that little instruction's been followed. We can see down here, number 8, 1, 2, 4, 8 LEDs up. So that's come out from the parallel port, and you see my screen has gone black and it's asking me to press any key. So you can see this gives us a clue what's going on here. We're actually converting this instruction in the background into the same kind of instructions as we were using before. So it does all the same thing, except on this kind of software, now we can do, it's much more easy to do what I'm going to show you next. I've written a little counting program now that can do a routine for us that will be much harder to do in machine code. It's possible to do it in assembly language and machine code, but it's a bit onerous because the computer likes to move RAM and information around and round to suit itself, and it's very difficult to force it to do exactly what you want to do. It's possible, but hard work. So let's be lazy. I've written a program a little bit earlier, just I don't want to use up too much time during the video. We've got a file here, and we'll open one I've written earlier. Let's have a look. It's down here, I think. It's a simple counting program. All it does is puts out, oh, here we go. Now, all we're going to do here is have a look at this program for a minute. You can see it's a lot more long-winded, but it does a lot more tricks. All we're doing here is these line numbers dictate the order in which this program runs. Now, I think in this particular version, we don't need them. It's a bit more like your normal C++ or high-level language. So long as the lines are above each other, that gives them the order to work in, unless you tell them any different. I'm just used to doing it this way because I don't do much of this stuff anymore. What we've done here then is we're starting off with a 0. We're putting it out. N is 0. Now we're going to put N out to the port. Then we're going to increment it once. And then we're going to stop at 256. So we want to say to the program, if we get to this number, then go to 50. That means we're going to stop. Otherwise, we're going to go on here to 100. Now you might wonder what on earth this little bit of the program is. This is to slow it down. If we were to run that program like that, it would go so fast, all you'd see is your lights flashing once and they'd all be on. It goes so fast you couldn't see it happening. So what we do is we put a little loop in here. This is just to waste time. This is just a time delay routine here. So we jump to the time delay and we count up to this number here, which is 10,000, and then we go back. Okay? We go back. Of course, if we haven't reached 1,000, we keep going round and round and round here 10,000 times, and then we go back to this program. That's just to make things slow enough for you to see them. Let's try and run this and see what happens. If you want to make it go faster, of course, you shorten the time loop. You just make this number less. If you want it to go slower, you make this number more. This is the number that your count stops at, and we'll just see how we go here. Let's try and run that now. We go to skip across here. We go to run and press enter to start, and you can see here it's still going quite quickly. All it's doing is counting from 0 to 256, or FF in hexadecimal, and then it's stopped. Okay, it's stopped there now. So we can go back up here now and have a good look at that. You can find out there's plenty of books and information on this old software. If you're writing C++, do it. I think I find it a lot harder to access the ports directly from C++. I don't know why that is, but you can jump around. You could actually write programs in this code and assemble it and call it out of C++. I think that's what all those DLL files do and driver files do in Windows and very high languages. So that's just an example of how we can use now a higher level software to assemble and run in the background. And as again you'd see before that ended, if we just run it again, here, you'll see the screen is going black. Okay, that's telling us that the computer now has jumped back in straight away. And it's finished. Press any key to continue. So we just go back to the higher level program. This is much easier now to use than the machine code for some aspects of your work, whatever it is you're doing. This will look something what you like in your C++ before you assemble it to run on one of these. You might be running it on that processor there, or you might be running it on that processor there. Your C++ assembler will detect or find out, or you tell it what you're doing with it, and it'll do the rest for you to get your program to run. So let's have a look now then at getting out of this, just to try out some of the other things that we've got here to show you that might interest you to play with. So we're going to have a look at the next one. We'll open one here. These are some I made earlier just to save you some time listening to me here. Now we've got input 889. Earlier on, I was showing you how we can input. If you remember, 889 that's a decimal number in this case. It's the same as 379. You remember we added one onto the output port address to get the register address for the data coming in from any printer on your parallel port. Let's have a look at this and see how we go. Go all the way around again. Not gone too far. You have to excuse me, there's no mouse in this game. Well, I could put a mouse on, but that's okay. I'm sort of used to doing this a bit. Now you